Okay, I wanted to review some of the updated information about this poster. Um, and so I've talked about the abstract and what is an ideal binary solution. That's this left-hand column. Let me start with the results and discussion. And this is the poster for ACS Spring 2026. And um, here we go. So this is figure 2. What you should know about figure 2 is that it is all data from the literature, and it's from 2, which is Sejo, Burgett, Munoz, and Marquez. Um, and um, I've plotted it according to delta ND max. That's the maximum difference in refractive index. Also can be referred to as the maximum non-ideality, um, meaning how non-ideal are the solutions. You can see over here that the dashed line is for ideal binary solutions, and the refractive index would be linear between the two pure components. Delta ND is the max. So this would be the actual data that you all collect, and this would be the difference that we're calculating. And we've got this, so that's the difference, the maximum difference in refractive index versus RB. RB is the volume ratio of the two molecules, where the B comes in, and it's defined down here. It is the van der Waals B constant for the N-alkane being varied versus the van der Waals B constant for the molecule being studied. And I have a whole separate video on why B is a volume called the co-volume. And also, one of the things you might get asked about this poster is why B? Why that volume? There are a number of different volumes you could use. And there's two things you can say. One is that information to obtain B is readily available for all the compounds that we need. And the other thing is that B, when we compared the co-volumes we obtained using B is a volume, um, and to other volumes, at least one other volume, we found that there was a better correlation for B than the regular old van der Waals volumes. That's the other volume we looked at. Anyway, another thing that's different from this, in this from other posters, is we did actually list the different alkanes. And so this graph is the maximum deviation, the change in refractive index, that's delta ND max, versus volume ratio of the two molecules, RB, for binary solutions of two N-alkanes based on literature data, that's reference to. And so N-pentane is the red, and you go down all the way to N-hexadecane, which is the pink. Fun fact, I've tried to do them in Roy G. Biv order, more or less. But what you can see is that figure 2 shows literature data for the relationship between delta, well, we just said that. We conclude that delta ND max is significantly correlated with RB, giving rise to a V-shaped trend with a minimum at RB equals 1. RB equals 1 we talk about next. So RB equals 1 is when the two alkanes would be the same size. And the only way we can do that is if it's just one molecule. It's not even a binary solution. So that's why there's no points at 1. But if there was, there's no non-ideality. Like, yes, there's no non-ideality because it's not, it's just a pure solution. Anyway, hopefully that makes sense. Um, and then the left branch is from the viewpoint of the longer alkane on the denominator. And so they're all the RB values are less than 1. And the right branch are for the shorter alkanes, where all the RB values, or most of them, are bigger than 1. Certainly for pentane, they're all bigger than 1. And certainly for hexadecane, they're all less than 1. Because hexadecane is the longest one, and pentane is the shortest. And then we say, so they're all positive, the delta ND max values, indicative of the fact that differences in alkyl chain length, and alkyl chain length is just a term of alkyl chain length is how many chains are in this alkane. So a chain meaning like C16 would have 16 carbons in a chain linked together. It's another way to refer to alkanes by alkyl chain length. And alkyl chain length of pentane would be 5. Alkyl chain length of C16 of hexadecane would be 16 carbons. All right. Differences in alkyl chain length give rise to higher values of ND than ideal due to more efficient or tighter packing of the two kinds of molecules. A similar correlation is found for the maximum deviation in density, delta rho max, that's rho, delta rho max as a function of RB. And that's one of the papers that we've currently got out and in need of review by me so that we can resubmit it. And then we go into why this is not surprising. It's something called the principle of congruence for binary solutions of two alkanes, which says that yes, there should be this type of pattern, and that at least one author in reference 6 has said that molecular volume would likely correlate with changes in excess molar volume, which is based on density changes. We're doing refractive index, and the thing you have to know about refractive index is that when density, so mass over volume, increases, for these solutions, refractive index increases as well. So it's actually very like we could make a very similar graph if we were doing what's called density or mass density. And somebody said you have to refer to it as regular old density from Chem 400 should be referred to as mass density, not just density, because there is electron density as well. And we are talking about refractive index, and refractive index that is higher for higher electron densities. Anyway, and our hypothesis is that when you that the alkanes are trying to pack more tightly because they can maximize their dispersion forces. We all know that alkanes have as their main type of intermolecular forces dispersion forces. And in Chem 400, we would say the only type of intermolecular force. And I think that's a good way to put it as well. Now, and so the smaller N-alkane will fill a void between the larger N-alkane molecules that will increase the density and increase the dispersion forces. And that's all literature data. And we did not do this at all. And we can be very clear about that. The only reason we're talking about this is because we're going to use it when we talk about the next part. Although this is new, all this is new. Delta ND max is new. Nobody has ever talked about delta ND max before. Though one person has talked, and there have been mentions of volume ratios. So delta ND max is really a new thing that we created, invented, came up with. All right. So the refractive index data that we did were collected for the propanol, pentanol, hexanol, and I'm missing a dash there for 1-decanol using our Abimat at 20.00 degrees Celsius. That's the best data. Other data was collected using an Anton Par SmartRef at between 18 and 22 degrees Celsius. That's good, but not as good data. For each data point in figure 3, refractive indices were measured at each tenth of a mole fraction, and the largest value of delta ND, regardless of mole fraction, was assigned as delta ND max. You might get this question, how did you find the delta ND max values? And what you can say is that when the chain lengths are similar, regardless of whether it's an alcohol and an alkane or an alkane and an alkane, that the mole fraction of delta ND max was typically 0.5. As they get very different in chain length, it tends to go closer to the longer chain length. That is the maximum value of delta ND. What we call delta ND max tends to be closer than could even be at a mole fraction of 70, 0.7 of the longer alkyl chain length, to use the term we've been talking about. Figure 3 shows our data for delta ND max versus RB for binary solutions of a primary alcohol and an alkane. First, the data strongly suggests V-shape. Yes. So that's now the colored ones here where we've reproduced the two alkane ones, the same data in figure 2, but the new data is for the different alcohols shown here. But now we're going to see that there is a negative section, but otherwise it looks very similar. So figure 3 shows our data. First, the data strongly suggest a V-shaped trend, similar to figure 2. Besides this similarity, there are two key differences. First, the minimum occurs at RB equals 1.3 to 1.5, depending upon the alkyl chain length of the alcohol. If we really zoom in here, you'll see that the minimum for 1-propanol is this red circle, and that the minimum for the decanol is this pink square. And you can see there's a difference there that does tend to change and get larger, or sorry, let's say this, get closer to 0. It's actually larger because it's a more positive, less negative value. So 1-propanol being more negative is more non-ideal at its maximum. Because delta ND max is always the one that's farthest from this line, whether it's a positive or a negative delta ND max. All right. So we're back down here. Second, we talked, right. Oh, I didn't show the 1.3 to 1.5. So 1.5 is about where the 1-decanol has its minimum. About 1.3 is where the 1-propanol has its minimum. And we're looking into that as well. So if you get questions, say, we're trying to understand that as well. Yes. And maybe I'll say some more about that this at the end. Those are the two key differences. Oh, and it's negative, and the RB is no longer at 1. Remember, RB was at 1 for 2 alkanes. And you can see RB right here for the hollow circles. In figure 3 at RB less than 1, the values of delta ND max for alkane alcohol solutions mirror the trend of delta ND max for alkane alkane solutions. So right here, they're steep decrease. They're not exactly on top of each other, but they're pretty close. That's what we mean by mirror the trend. We hypothesize that when the volume of the alkane is the same volume or smaller than the alcohol, that's when RB is less than 1, or equal to 1, as it says here, or equal to 1. The driving force for the positive delta ND max values is maximizing dispersion forces by allowing the smaller alkane to fill voids in the larger alcohol molecules. So same thing's happening. And for R greater than 2, It's not, yeah, please. Um, we also see a linear trend just like these. So we're saying at RB greater than 2, the same thing is happening. When it's more than double, when RB is equal to 2 or greater, the driving force for the positive delta ND max values is maximizing dispersion forces by allowing the smaller alcohol molecules, now the alcohol is smaller, to fill the voids between the larger alkane molecules. And then the next paragraph deals with this negative portion down here. And it says between 1 and 2 RB values, the values of delta ND max are for alkane alcohol solutions are negative. And I have done this on purpose. It's alkane divided by alcohol. So they are these type of solutions, but that's why it's greater than 2 means the alkane is greater than twice the volume of the alcohol. But between 1 and 2, sorry, we're talking about between 1 and 2 now. We hypothesize that each alcohol molecule takes up extra volume related to the presence of the alcohol group. As RB increases, the delta ND max values reach a minimum and start increasing between 1.3 to 1.5 RB. O1, the alcohol molecules are possibly able to fill voids between the larger alkane molecules once the alkane molecules become large enough. And what does large enough mean? Well, it depends on the alkyl chain length. But you can see here, eventually they do start going back up again. And we don't know. All we can know is, or all we can hypothesize is that that's true. That's our guess. And that's fun. So alcohol molecules are able to hydrogen bond with each other, generally known. Previous work has reported clustering of primary alcohol molecules in solutions with N-alkanes. Primary alcohol, by the way, I haven't said what that means. That means that on the alkyl chain, the alcohol's on the end. It's called a one alcohol. One refers to the fact that the OH alcohol is covalently bonded to the number 1 carbon, meaning the first one or the end one. So it is unclear to us, but a cluster of 2 alcohol molecules would have approximately an RB equal to 2. And so maybe that's what's happening, is maybe 2 of them on average are clustering together. And I think that's, so what else might we hear? I think that's largely what I wanted to say about this. Yeah, let's see.